Here's to anyone who's ever looked up. The airheads. And the space cases.
Live long and prosper.
The flight fanatics. The armchair astronauts. And the casually curious. Here's to those who know the thrust in newtons of a Pratt & Whitney J75 turbojet engine. And those who silently ask, what's keeping this thing in the air? Here's to those who can list the name, mission history, and favorite breakfast of every Mercury astronaut. And those who've ever searched for, how does a toilet work in space? Here's to the people who know a P-38 Lightning from a P-51 Mustang. And the people who thought those were the names of cars. Those captivated by the miracle of flight. And those who are just happy to make their flight. So whatever captures your curiosity.
We choose to go to the moon.
Or propels you to new heights. When it comes to the sky, there's space for all of us.
Good evening. I'm Chris Brown, and I have the privilege of serving as the John and Adrienne Mars Director of the Smithsonian's National Air and Space Museum. Welcome to tonight's Exploring Space lecture. I applaud those of you in the audience who joined us in person in spite of the weather and the rain. But this is, after all, a lecture about water. And to those joining us online, thank you for taking time this evening to be part of this lecture. This year's lecture series has featured oceans in our outer system. So far, we've learned about ocean worlds in the outer solar systems and the search for oceans on Mars. Tonight, we journey to our other planetary neighbor, Venus, to answer the question, did Venus ever have oceans? Frequently referred to as Earth's twin, though perhaps evil twin, is more appropriate given Venus's unforgiving environment, scientists often debate whether Venus was ever a watery world. After all, if it had oceans, where did the water go? In tonight's lecture, our distinguished speaker, Dr. Rita Parai, will give us some insights into these questions. But first, I'd like to extend our thanks to the sponsors of the Exploring Space Lecture Series. Tonight's program is made possible through the generous support of Aerojet Rocketdyne, an L3 Technologies company, and United Launch Alliance. Joining us in the audience tonight are Kristen Houston and Myra Montrose, representing Aerojet Rocketdyne, and Chris Root and Adi Basali, representing United Launch Alliance. Thank you, Kristen, Myra, Chris, and Adi, for your ongoing support. And to those of you here in person, I hope you've had the chance to explore some of our exhibitions before tonight's lecture. I'm very excited to share that 2 months from today, we will open 5 more galleries as part of our ongoing renovation. This includes the brand new exhibition, Futures in Space, a reimagined Baron Hilton Pioneers of Flight, and the return to display of many of our visitors' favorite artifacts like the Bell X-1, the North American X-15, and John Glenn's Friendship 7 capsule. We hope you'll come back to see these new exhibitions when they open on July 28th. And not to be outdone, the remaining galleries on the building's east end will all open, the entire museum will open on July 1st, 26, in time for the nation's 250th and the 50th anniversary of this museum. I hope you'll hold those dates and come visit to see yet again this reimagined national treasure. Now, I'd like to turn it over to my colleague, Dr. Emily Martin, a research geologist here in the museum's Center for Earth and Planetary Studies, who will introduce tonight's speaker. Thank you. Emily?
I have these very carefully crafted notes that have my name and position and department written down. So thanks, Chris. I'm now going to have to skip ahead. Good evening and welcome. Chris has already given an introduction to this lecture series, and I got really excited when I had an opportunity to participate in helping to organize this series, because it gives you the opportunity to design a theme for the lecture series. And oceans are my favorite research topic. And I do ocean work in the outer solar system, and I graciously helped design some additional lectures to focus on the inner solar system, where we also have a lot of oceans. You've probably seen Venus in the sky. It's the brightest thing you'll see in the sky after our moon, so you usually know when you're looking at it. It has a thick atmosphere. It's a similar size to Earth and one of our nearest neighbors. And it's maybe a bit of a surprise, because of all of those things that are so Earth-like, that Venus is so inhospitable now. But I've always wondered, what was Venus like before? What was it like early on in its lifetime? Because none of us are the same people we were when we were kids. And whether or not Venus was ever a watery world. Our speaker tonight, Dr. Rita Parai, is a leader in planetary science and an associate professor in earth and environmental and planetary sciences at Washington University in St. Louis. She's an expert in high precision, noble gas, isotopic analysis. Dr. Parai's work has advanced our understanding of the formation and evolution of planetary bodies, particularly the rocky ones like Earth, the Moon, and Venus. She is a co-investigator on the science team for the Apollo Next Generation Sample Analysis Program, and serves as the lead scientist for analyzing gases extracted from these pristine moon rocks returned by Apollo astronauts. Recognizing the importance and value of sample return missions, Dr. Parai has been actively involved as a science team member on multiple campaigns, advocating for sample return missions from Jupiter's moon Io and Venus, and maybe others. It is my pleasure to present Dr. Rita Parai.
All right, Emily, thank you for that introduction. So I am really excited to talk to you all today about this question: did Venus ever have a liquid water ocean? And so to start off, I'm going to tell you a bit about where I'm approaching this problem from and what I'll try to convince you of today. So I'm a noble gas geochemist. My research group uses a class of elements called the noble gases to study how planets form and evolve over time. So the noble gases are elements that are gaseous at Earth's surface temperature, and they are unreactive. So we call them noble because they don't associate with the riffraff of the rest of the periodic table. And so it might not be immediately obvious why you should study the chemistry of elements that are famous for not doing chemistry. But it turns out that noble gases are really important tracers of important compounds like water, carbon dioxide, and nitrogen, because they tend to go where water goes. And so noble gases will trace water through planetary reservoirs over time, and there are radioactive isotopes of other elements that decay to produce specific isotopes of noble gases that let us sort of put clocks on this transport of important elements like carbon, nitrogen, and a compound like water. So, hang on, I'll go back one slide before I put that there. So I've got a picture in the upper left here of my lab at Washington University. It's a noble gas laboratory. We take rocks and we crush them under vacuum, release gases that are trapped inside, and then we measure their isotopic compositions and their abundances using this mass spec on the right. And so we have a mass spectrometer that we bought, and then we built the rest of the instrument. It's not a common thing to have a noble gas laboratory, so a lot of these things are home-built, custom-built for the types of problems that we try to solve. And so what I'll try to convince you of today is that we really have a compelling need to measure the composition of Venus's atmosphere, both with a planned mission, the Da Vinci mission, and hopefully with a future sample return from the atmosphere to Venus that I'll tell you about. It's called VATMOS SR, Venus Atmospheric Sample Return, and I'm on that team. And the reason that we want to do this is that by combining measurements of the compositions of noble gases and other important gases in the atmosphere of Venus, we're seeking to understand why Venus and Earth look so different today. So this is part of a lecture series. I wanted to place us in context. If I make sort of a little spectrum of certainty about whether worlds have an ocean or had an ocean in the past, we have an ocean on Earth today. We've got a whole host of icy satellites, icy bodies in the outer solar system, moons of Jupiter, Saturn, Neptune, and then I put Pluto on there to be a little controversial, but we think that these all have a subsurface liquid ocean, liquid water ocean. So the last lecture was about Mars. We think that there's strong evidence for liquid water on the surface of Mars in the past, even though there's no liquid water on the surface of Mars today. And sort of as we're getting closer towards the sun in our solar system, I think our uncertainty increases a bit. For Venus, the answer right now is possibly, maybe. Maybe there was a liquid water ocean on Venus in the past. And so what I'll talk about today, why do we think that Venus may have had liquid water on its surface in the past? And then what would it mean for our understanding of our own planet Earth and for the habitability of other planets in our solar system and beyond? And so I'll start by talking about a little bit of the history of observations, what we learned about Venus, how we think about the science of what's dictating the conditions on Venus's surface, and then finally, what we need to answer and explore in order to have an answer to the question in the title of this talk. And so Venus and Earth, they're two planets of similar size, similar distance from the sun. Venus is sitting at about 70% of the distance between the sun and the Earth. And they both have atmospheres. You can see they both have clouds, but they have very different surface environments. So we learned about the surface of Venus over time. Here I'm giving kind of a truncated history of observation and exploration of Venus. It's not a complete list, but Venus was known since antiquity as a bright object in the sky. Its atmosphere was discovered in 1761 during a transit where Venus passed between the Earth and the sun. In the 1930s, spectroscopy showed that the atmosphere was made mostly of carbon dioxide, CO2. In the 1960s, sort of competing space agencies launched missions to explore Venus. So the Soviet space program had a series of Venera missions through the 60s, 70s, into the 80s. In the 60s, NASA had a number of Mariner flybys. And just some highlights, in 1970, Venera 7 was the first successful landing. 1975, we got the first image, which I'll show you on the next slide, from the surface of Venus. 1978, Pioneer Venus gave us some atmospheric probe data, among other data. And then in the 80s, you had more Venera missions, a couple of balloons, Vega 1 and 2. And then 1990 was the last NASA-led mission to Venus, Magellan. So this was an orbiter that mapped the whole surface using radar. And then the list gets pretty sparse. When I say that this is not a complete list, most of what I've skipped is actually on the left-hand side. The right side is pretty much exhaustive. So in the mid-2000s, Venus Express did a detailed study of the atmosphere. And then in the 2010s, we had Akatsuki, the Japanese Space Agency's JAXA's mission. So note that I don't have any 2020s entry on this timeline. And we're excited and hopeful for future exploration that I'll talk more about in the last third of the talk, these upcoming planned missions to try to answer urgent questions about Venus. All right, so let's look at some pictures. This first image from Venera 9, in the image here, you are seeing some beautiful rocks. As exploration of Venus was sort of spinning up, there was uncertainty about what the surface would seem like. Some people were hopeful for, lush forests, and I'm sure they were very disappointed by this. But as a geologist, I look at it and I'm like, yes, this is amazing. Rocks, just like our surface, is very relatable. And so in the early 80s, we got this Venera 14 panorama. And I should note that the curvature that you're seeing is kind of a fishbowl effect from the way that the image was taken. And so you can see the horizon kind of peeking out on the upper left and upper right corners. And what you see is kind of this flat, sort of rocky surface that's alien, but also kind of familiar. And so over this, I'm going to put a photo from the big island of Hawaii, where I am walking across a field of basalt. This was lava that was flowing out from the volcano, and it solidified to form a type of rock called basalt. And so the analyses of the surface rocks on Venus are consistent with basalt. They seem to be a similar composition, and so that already tells you something. Basalt forms on Earth when you have partial melting of this rocky layer that we call the mantle. And so the fact that you see basalt on Venus as well tells you that the composition of the rocky layer on Venus is going to be somewhat similar. And so that's one exciting similarity, but then so many differences. The surface of Venus has been described as hellish. And so the temperature is extremely high, 740 Kelvin, so in Fahrenheit, that's greater than 800 degrees Fahrenheit. These are pizza oven temperatures. And then in addition to the absolute blistering heat, there is crushing pressure. So about more than 90 times Earth's atmospheric pressure on the surface of Venus, and the composition of the atmosphere is very different. About 96% carbon dioxide, about 3% nitrogen, and then only traces of water. And the water that's present is present as a gas, as water vapor. If you were to take all the water vapor in Venus's atmosphere and condense it out into a liquid layer, that liquid layer would only be about an inch deep. And in contrast, if you did the same for Earth, took the oceans and the atmosphere, all the water in those layers and condensed them, that would be about 2 miles. And so it's much drier on Venus than it is on Earth. So in addition to all of these differences, there are also sulfuric acid clouds. I feel like I talk about the heat, the pressure, and once I get to the sulfuric acid, it's starting to sound really inhospitable, right? So you have sulfuric acid clouds that are very reflective. They reflect a lot of the incoming sunlight, which will be important later. The surface is very young. There aren't very many craters, and it is largely made of these basalt plains. So there's definitely not an ocean here now. Why do we think that there used to be, or could have been, an ocean there in the past? All right. So there are 2 lines of evidence that point us towards potentially having had an ocean on Venus in the past. First, a portion of the crust on Venus appears similar in its composition to a type of rock we call granite. Large volumes of granite only form where there is water. The second line of evidence is a geochemical one. The atmosphere of Venus is strongly depleted in the light isotope of hydrogen. So I'm going to illustrate what that means in an upcoming slide. And we call this a high ratio of deuterium to hydrogen, or D to H. And that's a signature of having lost water. And so let's dive into these 2 lines of evidence. So I'm showing a global map from the Magellan orbiter on the left, and there are regions of terrain that are anomalous terrain. If we sort of zoom in on that spot indicated by the arrow, it looks like the picture or the image on the right. And so we are looking at dark, smooth basalt plains with a strong contrast to these anomalous regions that we call tessera. So the tessera are bright, they're rough, they're clearly made of something different. And based on the emissivity of light from these tessera regions, we think that they could be made of a granite-like rock. And so the same image is shown on the left here, and then in the center and on the right, I'm showing two types of rock, basalt, which we talked about before, and granite. So the same type of granite you have in granite countertops. The compositions of these rocks are very different. In the basalt, you have a lot of magnesium, iron. In the granite, you would have more of potassium, aluminum, sodium, silicon. Large volumes of granite are only made where water is present. You can make a little bit of granite without water, but it's hard to make large volumes without water present. So on Earth, granites are made at places we call subduction zones, where two tectonic plates are converging, one dives underneath the other, it releases some water that it picked up during its lifetime at the surface, and that release of water into the overlying mantle helps a series of events that produces a granite. And so if we see granites on the surface of Venus, perhaps something similar happened there in the past. The other line of evidence is the strange isotopic composition of hydrogen in the atmosphere of Venus. And so when we're talking about atomic structure, you have the nucleus of an atom that's made up of protons and neutrons. The number of protons determines what element you have, and then you can have differing numbers of neutrons that would give you a heavier or lighter isotope. You have a cloud of electrons orbiting around that nucleus. And so in the red on the top left, I'm showing normal hydrogen. It's just one proton in the nucleus, one electron orbiting around it. The heavy isotope of hydrogen has that one proton and a little buddy, a neutron, in that nucleus, and so this is a heavier isotope of the same element. So on Earth, the ratio of these two isotopes of hydrogen is about 1 deuterium for about 7,000 regular hydrogens. That's similar to what you find in rocky asteroids. It's similar to the building blocks of what we think would have made our rocky terrestrial planets. Venus has about 120 times more deuteriums per hydrogen, a lot more of that heavy isotope of hydrogen. And so you can get that if you have preferentially lost the light isotope somehow. And so the mechanism for producing this signature is if you have a really hot atmosphere. If the atmosphere is very hot, all the water is present as water vapor, so it's a steam atmosphere. At high temperatures, that steam is present at high altitudes, so high up above the surface, where it can interact with sunlight. And ultraviolet sunlight interacts with water molecules in a way that breaks them apart. We call this photodissociation. And so that photodissociation liberates hydrogen, which is then light enough to escape from Venus's gravity. So this process preferentially acts on the light isotope of hydrogen. And so you preferentially lose the light hydrogen, the remnant atmosphere becomes enriched in the heavy isotope deuterium. And so that's how you get a high D to H ratio in the atmosphere of Venus. And so what that tells us is that high D to H is a signature of water loss. Why did this loss occur on Venus and not on Earth? We think that the mechanism depends on having a high temperature, high enough to put steam at high altitudes in the atmosphere. So if we want to understand how Venus lost its H2O, which at this point we don't know if it was ever liquid water or just always water vapor, if we want to know how it was lost, we need to understand what generates such high surface temperatures on Venus. Now you might have a sort of intuitive feeling, oh, Venus is closer to the sun. That's how I always start thinking, right? Venus is closer to the sun. Maybe that's why it's hotter. No, that's actually not the reason. So to understand the reason that the surface of Venus is so much hotter, we need to think about energy balance on planetary surfaces and the interaction between light and the composition of the atmosphere. So this is something that I like to explain in sort of 3 beats. So if you'll bear with me, we're going to do column 1, column 2, column 3. We're going to talk first about how warm things emit light. And the amount of light and the type of light depends on the temperature of the thing. The second story beat to understanding why there's a high surface temperature on Venus is thinking about the balance between reflected light, absorbed light, and emitted light. And then the last story beat is the greenhouse effect. So thing number one, warm things emit light. Light is one of the ways that energy is transmitted through the universe. When I say the amount of light, I'm showing a plot where the vertical axis is the radiance. So you can think of that as the amount of light. And then when I say type of light, I'm referring to the wavelength of the light. We're familiar with the visible range of the spectrum. This is wavelengths of light that our eyes can detect. So the longest wavelength of light that our eyes can detect appears to us as red. And then as you go towards the shorter wavelengths to the left, you progress across the rainbow to violet. And so if you have light with a shorter wavelength than violet, we call that ultraviolet, beyond violet light. On the other side of the spectrum, if you have something with a slightly longer wavelength than red, we call that infrared, beneath red. There are other regions of the spectrum that have other special names, but we're not going to talk about them today, so just wanted to define these for you here. So the critical thing is that the amount of light emitted by an object for different wavelengths of light is going to be depending only on its temperature. So for an object with a temperature of 5,500 Kelvin, so that's the temperature that we think is at the surface of the sun, you'll have a profile like what's shown in green here. So there's a peak in the radiance that's in the visible range, and then the amount of light that's emitted at other wavelengths tails off as you move away from that peak. Now, if I add two curves to this showing two cooler objects, still these are star temperatures, we're still talking about very, very hot things. So showing these two cooler temperatures, you notice two things. The cooler bodies, the peak radiance shifts to longer wavelengths, and less light is emitted at every wavelength. And so these are two important things. When we go from stars emitting light down to planets emitting light, the planets are much, much cooler, right? And so the planets are going to show up at much longer wavelengths. Their peak radiance will be at much longer wavelengths in the infrared. They're also going to be way, way low on the vertical axis in terms of how much light they emit compared to stars, because they're much cooler. And so on this next slide, I'm going to zoom out on the horizontal axis. So instead of 0 to 6, I'm going to go to from 0 to 48. And on the vertical axis, I'm going to zoom in to the bottom fraction of a percent and show you some planetary curves here. So same radiance versus wavelength of light, and now we're looking at orange curve for something that's the temperature of Venus's surface, around 750 Kelvin. And so its peak is in the infrared range. You can see the visible range squished all the way to the left on this zoomed out horizontal axis. And the important thing to note here is that between a cool planet and a very hot planet, there's this very dramatic difference in how much light is emitted from the surface. So I could zoom in one more time to show you that Earth curve that's barely visible in that last slide. Now you see something that's about 300 Kelvin, that's Earth's surface-ish temperature. And now the Venus curve is way off scale. So much more light emitted on a hot planet compared to a cool planet. All the peaks for the planets are in the infrared range, and then the stars, their peaks are in the visible range. Those are the important things from beat 1. All right, column number 2. Light can be reflected, absorbed, or emitted, and the balance between these things matters for how the temperature of an object changes. And so the balance between light that is emitted and absorbed determines whether the temperature of the object is going to change. If energy in equals energy out, so absorbed equals emitted, then you have a constant temperature. If energy in exceeds energy out, the temperature is going to rise. And so I have this thought experiment where I've drawn a little wooden table upon which I've placed a block of something, and it's in thermal equilibrium with the room, it's at room temperature, it's absorbing some light, it's emitting some light. It's at a constant temperature, and then I decide to stir things up. I turn on a lamp. I turn on one of those heat lamps like caterers have to keep your food warm, and all of a sudden I have added light, some of which is reflected off the surface, but some of which is absorbed. And for a moment, the energy in exceeds the energy out. and so the temperature of the block increases. So what happens to the light that it emits? It starts to glow brighter. So it starts to emit more light, and its peak radiance shifts a little bit towards shorter wavelengths. So it'll keep increasing its temperature until it reaches a new balance, where now it's hot enough, it's glowing bright enough, that its emission balances its absorption. And so we can do the same thing for a planetary surface. So we're still on column number 2, but now we're thinking about planets. So for Earth, when we think about the incoming light, this is light from the sun. And all the units here are going to be in watts per square meter. So you think about your 100-watt light bulb, the number of watts per square meter from the sun, this is globally averaged at the top of the atmosphere, is 340 watts per square meter on the Earth. And about a third of that is reflected. So reflected off the tops of clouds, off of different surfaces on the land, and out to space. 240 watts per square meter are absorbed. And so the surface at a stable temperature is going to emit 240 watts per square meter through the atmosphere and partially from the atmosphere out to space to balance that absorbed energy. Now on Venus, it's closer to the sun, so it's picking up more watts per square meter. And so a higher number of watts per square meter, but much more of that is reflected by these sulfuric acid clouds. And so even though Venus is closer to the sun, the highly reflective clouds mean that less of the light is absorbed and emitted from the surface compared to Earth. And so having these very reflective clouds mean only that only 160 watts per square meter are absorbed and emitted. And so you'd look at that and be like, wait a second, why is Venus so hot? And so the last column, the greenhouse effect, is the way that we explain this and understand this. And so the greenhouse effect, greenhouse gases like carbon dioxide, methane, water, these are all molecules that absorb infrared light. They don't absorb visible light. Visible light doesn't care about greenhouse gases don't care about visible light. And so it's the infrared light emitted from these cooler planets that are affected by greenhouse gases. And so in this cartoon here, I've drawn infrared light that's being emitted from a planetary surface. As it's making its way through the atmosphere, I'm going to make my little CO2 molecules dance. We ask the question, how far can it travel before it encounters a CO2 molecule? And so if I let these sort of float around, all right, my infrared light has encountered a CO2 molecule, it gets absorbed. And so that CO2 molecule is momentarily excited, and then eventually it will re-emit that infrared light. But then it's rolling a dice. Which direction is it going to re-emit that light in? It could re-emit the light in a way that would send it back out to space, in which case that light just sort of paused for a moment, or it could re-emit it down towards the surface, where it would be reabsorbed by the surface. And so the more CO2 in the atmosphere, the higher the likelihood that infrared light will be absorbed and re-emitted back down towards the surface. And so if we tie that back together, go back to this diagram, the reason that the surface temperature of Venus is so hot is that Venus needs to basically glow brightly to get infrared light through the atmosphere. So you can imagine if Venus had a cooler surface, it would emit a smaller amount of infrared light, our orange versus our blue curves on that first plot. And some proportion of that would be absorbed and re-emitted downwards. It would be absorbed by the planet. It wouldn't get out to space. And so energy in would exceed energy out because the incoming light is in the visible range of the spectrum. It doesn't care about the CO2 atmosphere. And so your temperature would increase and increase and increase until the surface was hot enough that the amount of infrared light that passes through the atmosphere and makes it out to space balances the incoming light from the sun. And so that's why it's so hot on Venus. That's why you could get a steam atmosphere with a lot of H2O at high altitudes that could photodissociate and be lost to space. And so that sort of shifts our question from what drove the water off of Venus to what gave us this extreme greenhouse on Venus. Is the atmosphere of Venus unusually CO2 rich is a good place to start. If you do a comparison of the budgets of carbon on the surfaces of Venus, Earth, and Mars, there's this really interesting observation that Venus has a certain amount of carbon as CO2 in its atmosphere. It's very similar to the amount of carbon that is stored as rocks in the crust of the Earth. And so it may not be the case that Venus has an unusually CO2-rich atmosphere. It may be the case that Earth did something funny early in its history to trap all of that CO2 as carbonate rocks. And so understanding what made Venus take such a different path from Earth is really important. Did Venus always have an extreme greenhouse? Did it arise at some point in its history? And then did it arise by chance? Was there some chance event that led to this? Or is this like a determinative thing where it's an inevitable outcome of having a planet at that distance from its star that this will turn into an extreme greenhouse situation? And so the key to understanding, understanding this is the key to understanding planetary habitability in our solar system and then beyond when we think about exoplanets orbiting around other stars. All right, so I wanted to summarize the competing hypotheses for when Venus lost its water, when this extreme greenhouse was set up, and I'll introduce these thoughts and then sort of note my reaction to them. So the first hypothesis, Venus never had an ocean in all of its 4.5 billion year history. So in most of these models, you start off the planet as a barren rock with no atmosphere, and then volcanic activity adds gas to the atmosphere over time. And if this is the case, you have this runaway greenhouse where you never have the pressure and temperature conditions to condense liquid water. The second sort of line of argument is that Venus did have an ocean early on, but it was very short-lived. That it lasted less than 1 billion years. I know that doesn't sound short-lived, but in the history of the solar system, that's not that long. And then the third had an ocean early on, and most of its history, that ocean was there, the surface was clement, and then it was only recently that something happened to make Venus inhospitable. And so I've summarized these three, and then when you take a step back, you're kind of like, wait, these are all of the options. It's like, this has covered every possibility. The only thing that might be missing from this list is it had an ocean and it stopped halfway through solar system history. We've got it, had it, never had it early on, had it late. Okay, so what this underlines to me is the need for new observations and new missions to explore Venus, because we have more questions than data to help constrain them. And so a list of these questions, I won't belabor this since it's an all-text slide, but there's so many interesting questions that we have to get at to answer the big overarching question of how, when, and why did Venus lose its H2O, its water. So things that are important, we want to understand what materials contributed to the growth of the planet. What sorts of elements did they deliver to an early atmosphere as Venus was growing? During the growth of the planet, did we have giant impacts, these energetic collisions between growing planetary bodies that could melt or even vaporize the growing planet? They could form a magma ocean, a totally molten layer on the growing planet. How did volcanic activity over time change the distribution of different gases between the interiors? There's gas trapped in every planetary interior, and gas that's at the surface in the atmosphere. What chemical reactions happen in different layers of the atmosphere, and could those have been different in the past? And then a final question that I want to highlight, there's so many more, but what role do the physical properties like the rotation rate play in the evolution or the survival of oceans or atmospheres on planets? So planned exploration missions to Venus. This is a list, and then I'm going to talk a little bit about one of them. So there are 2 missions that are in development as part of the Discovery program through NASA. There's Veritas and Da Vinci. I'll talk a bit about Da Vinci. The European Space Agency is planning an orbiter called Envision, and then Roscosmos is planning an orbiter, lander, and balloon called Venera-D. And then the Indian Space Agency, ISRO, is planning an orbiter called Shukriyan. So I will talk a little bit about Da Vinci because I really want to highlight the need for atmospheric measurements. So based on the small number of craters compared to Mars or the Moon, we think that the surface of Venus is young because there was a global resurfacing event. So a huge outpouring of volcanism that gave you this smooth basalt plains that you see on the surface today. And so that's thought to have occurred somewhere between 250 million years ago and 750 million years ago. So the surface is relatively young. That also means that the geologic record of about 90% of Venus's history has been erased. And so we can't do the sort of studies that we do with rovers on Mars, where you're looking at these successions of geology, basically going backwards through time. Luckily, the history of Venus's evolution and its formation was recorded in the atmosphere. So an analogy that I like to think of is a teenager throwing a house party while their parents are away. So no matter how much work they do to set things back in place and clean everything fastidiously, when the parents come back, the house doesn't smell the same. A party was had at this house, they know exactly what's happening here. The atmosphere is like that on planetary bodies. They are constantly recording the processes that the planet goes through, and so the atmospheric composition holds this record for us that the geological record no longer holds. And so I think about planetary atmospheres. I think about three things. The atmosphere of a planet, we need to think about what was delivered during its formation, which we call accretion. We need to think about what mix of rocky asteroids versus icy comets delivered gas to this early atmosphere. And so that's the arrow pointing down from space. I've got an arrow pointing up from that volcano, volcanic outgassing over time. What was transported out of the interior into the atmosphere? And then lastly, what was lost to space and when? And so this is my noble gas, 2 slides on noble gases. The reason that we study noble gases and we're excited about them is that they trace volatile origins and transport. Every noble gas element has at least one isotope that's produced by radioactive decay. I've got this glowing electric green to color code those. And then at least one isotope that's not produced over time. I have a very soothing purple to color code those. And so the point of showing you this table of isotopes is not for you to memorize them or absorb really any information except for the visual that every element, helium, neon, argon, krypton, xenon, has at least one isotope produced by radioactive decay and at least one that's not. And so what that lets us do is address each of these three questions, each of these 3 arrows. For the delivery, ratios of primordial isotopes, they're like fingerprints. Rocky asteroids versus icy comets versus, say, solar gas. These all have very different abundance patterns for these primordial isotopes. And so you can measure what's in the atmosphere and try to interpret that as, oh, okay, this could be a mix of like 80-20 rocky asteroid, cometary, icy comet mix. So that's telling us about delivery. When we look at the things produced by radioactive decay, the radioactive isotopes are all things that like to live in rocks: uranium, thorium, potassium. Those will live in the interior and they'll produce those bright green isotopes over time. And depending on the rate of volcanic outgassing, you will change the composition of the atmosphere with this really distinctive, think of it as green-colored gas added to the atmosphere. And so you get clocks for that volcanic outgassing. And then lastly, there is one element that seems to be really sensitive to loss to space. Xenon isotopes in the atmosphere of Mars and the Earth both have an enrichment in heavy isotopes that we think has to do with hydrogen loss from these atmospheres. And so you'd predict to see that signature also in the atmosphere of Venus. And so it would be great to be able to make these measurements in samples of the atmosphere and try to address these 3 different questions, these 3 different areas with the noble gases. And so the mission that's in development, Da Vinci, this is selected as part of the Discovery Program, the Deep Atmosphere of Venus Investigation of Noble Gases, Chemistry, and Imaging mission. It includes this descent sphere, where the plan is to take continuous measurements as this descends through the atmosphere of Venus, which I think is so cool, and I think would be really exciting to have this in situ measurement. Now, the best that we can do in an in situ measurement is different from the best that you can do in a terrestrial lab, because you have to consider trade-offs. There are power considerations. There's what you can do in a limited amount of time in a spacecraft that's flown to another planetary body, right? It's crazy. And so the other thing that I'll briefly talk about is this mission concept that I'm a part of, Venus Atmospheric Sample Return, where you could have, in the brief time of just 1 year, a sample returned from Venus. So this is an example of the orbit. I won't go too far into it. But the idea is that we would launch something from the Earth. It would pass through the atmosphere of Venus, collect an atmospheric sample, and then return it to the Earth for analysis. This would be the first sample returned from another planet. It would pass through the atmosphere in the well-mixed layer, and then return that sample to Earth to be analyzed with cutting-edge instrumentation in labs across the globe. There are challenges to it. There's a question about sampling at high velocity. Are you getting the same composition or a different composition from what's actually in the atmosphere? And if so, can you model it and correct for it? There are trade-offs between getting into that well-mixed layer versus fuel needs. And then there's the question of having a heat shield that works twice. That's not been done before. And so you need the heat shield to work at Venus and then work again on Earth. And so to conclude, I'll just say Venus may have once had oceans. A high D to H ratio tells us that we had water or had H2O and lost it. It doesn't tell us whether it was liquid water or gaseous. The different models and arguments that we have really highlight the need for new observations, new missions to explore this sister planet that we have that is so intriguingly different from our own. And so I will just end by thanking our sponsors, Aerojet Rocketdyne and the United Launch Alliance, my collaborators, Guy Avis, Christophe Satin, and Jason Rabinovich as part of the Vatmos SR team. And then my parents, who are here tonight, dug up this photo from, hi, my parents. Dug up this photo from our first trip to the Air and Space Museum in August of 1990. So thanks, Mom and Dad, A, for bringing me here, to the Air and Space Museum and generally into the world, into being. But I noted that this was August 1990, which is also when Magellan, the last NASA-led mission, started its operations around Venus. And so it's our time, right? This generation has come up. It's time to explore Venus again. And so a huge thanks to the Smithsonian National Air and Space Museum for the work that you guys do to educate and inspire people of all ages. Thanks.
Okay, this is my favorite part, is the question part. So if you have questions, which I'm certain you do, because you can't tell me you don't after that, there's a QR code up here. I've been sending in questions all night. Please use it. It's very simple, I swear. You don't need an account or anything. Just do that, send in your questions, and they'll come right here. It's almost like it's bottom heavy. Thank you for that. I'm so excited. I have a couple colleagues that work on Venus, and I ask them all kinds of impertinent questions all the time. So the first question I want to ask you has to do with those D to H ratios. And you said this really well on your conclusion slide. It tells us there was water. There's a lot more questions we have to answer before we know anything about oceans.
That's right.
So instead of asking you a chemistry question, I want to ask you a geology question. The surface of Venus is super duper young, and on places like Mars, we use that geology the way it looks to say something about, oh, look, maybe there was water here, because you could form that kind of structure that way.
Right.
Any geological evidence?
So I think investigating the tessera in depth are going to be critical for that. So this emissivity that hints that these might be granitic type of rock. If you had granites, that's hinting that you had something like subduction, or at least an ocean that would have hydrated rocks at the surface. And so you could make compositions of rocks that had, or minerals that had compositions that took bound water and trapped them in their mineral structure. So I think that would be sort of the thing to focus
Awesome.
on.
Okay, right. I really love this question because I think it brings up a lot of challenges in exploring Venus. Would Venus ever be a candidate for something like a rover, lander kind of situation? I know we talked about the Venera spacecraft from the USSR at the time. Could we do it? Are we there yet?
I'm not sure that we're there yet, but I also think that we shouldn't be restricted to thinking about what has been done on other planets before, especially as we're moving towards kind of these copters on Mars and on Titan in the future. And so there are lots of mission concepts about balloons that could float at different heights in Venus's atmosphere and explore in this way. And I think that there's a lot of science that you could do from such a platform. In terms of a rover, I think that would be so awesome. It would be so awesome. And I think there's a lot of technological development that's been done and continues to be done to try to get materials that could be have some longevity at the surface conditions on Venus. Yeah.
Okay, I have so many more questions. Keep sending them in. You guys are doing great. You do a lot of sample science, and we asked you to come here and tell us about Venus, which we don't have a lot of samples of,
Yes.
if at all. Can you talk a little bit about how some of the work that you do in your lab on rocks from Earth, rocks from Moon, and how it helps you be a Venus scientist? How does it help you learn more about Venus?
Yes, absolutely. So I run this lab where mostly, I'd say 95% of the samples that we're running are terrestrial rocks. They're volcanic rocks, and we're treating Earth as a planet, trying to understand all the same questions. What mix of materials delivered water, carbon, nitrogen, and noble gases to the growing planetary body, and then how did they get shuffled around over time? And so I see them as sort of things that we wish we could do with Venus rocks. And since we have this much greater accessibility of terrestrial rocks and a very interesting planet that we happen to live on, we're doing them here. But I think they're also setting up our understanding of what are typical gas contents for volcanic samples. What could we expect in a rock from X, Y, or Z setting, and how should we plan for sampling? How should we plan for curation? How do you handle these samples in a way that preserves their gas content as it was upon sampling?
So I'm going to ask you a really, hopefully softball question. Can you talk a little bit about how you can study atmospheres and atmospheric gases when you're holding a rock? Can you like divulge that super cool geology secret to everybody?
Sure. So for the terrestrial samples, we're actually trying really hard not to measure terrestrial atmosphere and fighting a losing battle a lot of the time. So we're trying to measure magmatic gases that are trapped in volcanic rocks. And so with that, you have a volcanic rock that has sat at Earth's surface for some amount of time. It's gotten contaminated with the atmospheric gas. And I was talking to a friend earlier about how my initial interest in Earth and planetary science was very focused on the deepest part of the Earth. I was like, oh, and we were talking earlier about this as well, that the deep interior was really inspiring and interesting to me. And I've kind of been, not dragged, but I have made my way
flying your way up
towards the surface, because what one realizes is that the interior of a planet and its atmosphere are intimately connected. They are constantly exchanging gas. On most planets, you have volcanic outgassing. It's just a one-way arrow taking interior gas and putting it into the atmosphere. On Earth, we actually have the arrow going back in with subduction carrying atmospheric gas into the interior.
I feel like this is the quintessential question we get when we have visitors come into the museum and we're showing them Martian meteorites, right? And meteorites from the moon, and everybody says, but how do you know this is where it's from? And so we always get to give them the whole, like, you know, the secret geology where it's like, hey, you trap the gases inside the rock. And no, it's wild, but...
It's a famous noble gas story. So the Martian atmospheric noble gases that were measured by a spacecraft match what's in these Martian meteorites.
Now you know. You can impress all your friends the next party you go to. We know Earth didn't necessarily start off its life in its current exact distance from the sun. And the sun wasn't, the same star it was 4 billion years ago. What do we know about Venus's position in the solar system today? Has that changed a lot with time? Do we know if that's changed a lot with time? Does that even matter in this case?
So the sorts of things that go into the models of past Venus climate have to do with difference in the brightness of the sun, how much sunlight Venus is receiving, potential difference in the rotation rate. So these orbital characteristics and the amount of sunlight that it's receiving, those are very important to understanding what Venus was like in the past. We think that the sun would have been fainter billions of years ago, or 3 billion years ago, for instance, than it is today. And so on Earth, this is called the faint young sun problem, and we hypothesize that maybe greenhouse gases offset that difference for some planets. So a similar thing for Venus. The rotation rate, I think, is a really interesting question because that seems to be very important for the longevity of an ocean on a hypothetical model planet.
Challenge question. Venus basalts are really young. Surface of Venus is really young. What do we know about how basalts cool when they're cooling to pizza oven temperatures?
This is such a good question.
Challenge question. I think the answer is, but I'm curious what you think.
Well, we need experiments. So there are a couple of things. The pressure is so high on the surface of Venus that it is similar to a submarine eruption, but the temperature is also extremely high. And so you almost wonder if you would get a much slower cooling. It's not sort of high enough that you would get coarse-grained, I think, anything. But you could have a very different texture to the rock, and that could affect things like how does it break? How does it erode over time?
I have so many more questions about that, but I think they're all open-ended, so we're just going to move on. Can you talk a little bit about remote sensing of things like noble gases and some of the other isotopes and isotopic ratios? You can tell it's not a geochemist. I'm struggling over here. How do you remotely sense those? So with a lot of the other spacecraft that have gone to Venus or are going to Venus that are simply going to be orbiting, what can we measure? What can't we measure?
So I think noble gases all fall in we cannot measure these through remote sensing. So they are not easily detected in that way. And so it's a mass spectrometer that's needed to measure the noble gases.
Okay, philosophical question. Hopefully somebody in the audience had the question going on in their head of, we've had a dearth of missions going to Venus recently, and now all of a sudden we have an enormous group of international missions that are going to Venus in, let's say, the next 10-ish years. Can you talk a little bit from your perspective about why that's a good thing, why that's not redundant, why that's a huge opportunity for answering some of these big questions for Venus?
Yes, absolutely. So all of these missions have a different focus, and they all sort of play off of each other to help address, when I have that list of sub-questions, these are all things where we need this puzzle piece, we need this puzzle piece, we need to all bring it together to try to answer the overarching question. And so I'd say absolutely not redundant. These are all missions that are focusing on different important parts of better understanding Venus.
Awesome. Thank you so much for being here. It's been so wonderful to have this literal dive into ocean and atmospheres. There's like so many different plays on word there, into Venus. This was really exciting. So thank you for being here. I also want to once again thank our sponsors, L3 Harris and United Launch Alliance, for supporting this Exploring Space lecture series. We literally can't do this without you, so thank you so much for that. Unfortunately, because we had to bring the water from the sky tonight to fit the theme of the party this evening, there is no sidewalk stargazing. So sorry. I know it's really fun to do. We want to thank all of you for coming out, braving the weather, and joining us tonight. We really hope to see you at our final Exploring Space lecture of 2025, which is happening on June 18th, where we're going to explore the question, what happened to Earth to get all of these amazing liquid water oceans that we have on this planet that we all love to enjoy. So thank you so much. Good night, and please be safe.